This is our final lecture on Floquet engineering. It's our 5th lecture this week. And the plan for today is to continue from where we left yesterday. We were starting to discuss the Anderson-Kondo model, and we are going to see how to Floquet engineer this model. So just putting our topic here, we are still Floquet engineering. We are still Floquet engineering, and now we're talking about strongly correlated systems. Strongly correlated systems. And yesterday we were able to start and finish the case of the Hubbard model leading to the Heisenberg model. And in today's lecture, we are going to finish the example number 2, that was the Anderson model, leading to the Kondo model, but leading to an effective Kondo model that is going to have the help of a Floquet field. Same way as topic number 1 was the Hubbard model leading to the Heisenberg model. So that's what we are planning on doing today. I will start with the so-called Anderson impurity model. Anderson impurity model. And then I will show you results for Kondo lattices, in which we have a lattice of impurities. So it's not, these are not impurities anymore. It's just a lattice of, for example, Syrian atoms or praseodymium atoms. Okay, so the simplest case that we can treat here consists of a chain. Let's say that we have a chain here. So these are left electrons, and these are conduction electrons. And then here we have the right electrons, so R electrons. They are also conduction electrons. And then I put some impurity site here in the middle that is going to be a quantum dot, basically. So this is our impurity site. Impurity site. And the idea is that we have strong interactions here inside this dot, but the conduction electrons don't interact strongly. So we can just consider these non-interacting conduction electrons moving around here. So you have electrons moving around here and here, but they can talk to this site. If they decide to talk to this site, they are going to face some penalties. They are going to have a different type of chemical potential, a different value for the chemical potential inside this atom, or the on-site energy here is very different. And you also pay Coulomb repulsion. So let me write down what is the Hamiltonian for this. So far, I'm just writing down a microscopic Hamiltonian that is called the Anderson single impurity model in 1 dimension. That's all I'm doing. So the Hamiltonian has the following form. This is also called leads. These are also called leads. These are reservoirs of conduction electrons. This is when you have a quantum dot, you connect these 2 gates, and these are these left and right moving electrons, or these electrons to the right and the electrons to the left, corresponding to these reservoirs of conduction electrons. These are not chiral electrons at all. It's just that these electrons are to the left and these electrons are to the right of this dot, okay? All right, so what is the lead Hamiltonian? It's the hopping term. We wrote the hopping term many times. And now we have 2 flavors, left and right electrons. So I'm going to call this alpha. And for each of them, I'm going to sum from 0 to infinity, and I'm going to sum over sigma AI alpha sigma dagger AI plus 1 alpha sigma plus Hermitian conjugate. Our good old 1-dimensional chain with 3 electrons, okay? One of the simplest possible problems that you can solve. And now, I'm going to let these electrons, that can be the left or the right electrons, to talk to this impurity site. So the way it talks to this impurity site is by this hybridization term. We call it hybridization term. It's just hopping, but now hopping to this yellow dot. So alpha can be right or left, sigma, C sigma dagger, A0. This is a 0, let me write it down, because I'm going to, so this is site 0, okay? When this talks to this guy. So this is 0, and this is also a 0. But this is 0 to the right and 0 to the left. And you start count. If you look at this Hamiltonian, you start counting like this. You count like this, and then you count like this, your sites, okay? 0 plus Hermitian conjugate. So this is called the hybridization. So notice that we have, oh, sorry, A0 alpha, yes, thank you. A0 alpha sigma, A0 alpha sigma, thank you. A0 alpha. So we have the AI, let's say, alpha sigma. These are going to be the conduction electrons. And we have our C sigma that is going to be our impurity. It's going to label our impurity. So this is the C. If I define N sigma as the number of electrons of C type, so this is just a definition, I will also have, additionally to the H lead and H hybridization, the Coulomb price that I told you that has to be paid here. The Coulomb price of this quantum dot is going to be U, the Hubbard U, N up and down, okay, N up and down, plus epsilon F, N up plus N down. This is the chemical potential difference, if you will, or on-site energy difference of this dot, of this impurity, as compared to the conduction levels, okay? The idea here, so far this is the Anderson model, you can solve it, quite interesting. But as it was the case with the Hubbard model, I'm interested in understanding the low energy physics. So the low energy physics, the limit here, so the limit that I will try to understand that reproduces this Kondo model is the limit in which U goes to infinity. So I cannot allow double occupancy of this dot. It can host one electron. And that epsilon F is large in magnitude, and negative. And negative, okay? Notice that this is quite similar to what we had from the Hubbard to the Heisenberg model. These two things can be basically unified if you think of both of these low energy models coming from Schrieffer-Wolff transformations of the respective Hubbard and Anderson models. Okay, I'm doing them one by one. This one, we learned typically Hubbard models before the Anderson model, so I'm doing both of them more or less carefully. So in this limit, if I just completely neglect V, this dot is disconnected to the rest of the chain. One electron sits there, and life is good. And boring and good. So you have conduction electrons moving around here, one electron sitting here, and the electrons moving here. Great. But what I want to do is I want to allow V to be small and finite. What does it mean to be small? Again, V divided by epsilon F is much less than 1 but finite. Okay? And then I have to write down what is the low energy model for this in this particular limit. And this is the part that I won't have time to do, but under this assumption, you do the so-called Schrieffer-Wolff transformation. It's called, it's in any strongly correlated textbook, like Fetter and Valechka, Coleman, Bruce. You can find them. It's a pretty standard transformation. It will lead to the effective Kondo model, which has a JK, as I wrote yesterday. Sum. This is not even going to be a sum. I can just write down that at site 0, you're going to have an effective spin. So this is the effective spin. Talking to the C of conduction electrons at that particular site. So sum over alpha, let's say C0 alpha, or the conduction electron I'm calling A. So it's going to be A0 sigma alpha, or even alpha, but then I have to put the spin index here, A0, let me put it I and J, here IJ, 0 alpha J. okay? Where I and J are Pauli matrix indices. So the effective spin talks. Exactly. This is sum over, yes, alpha and I and J they have to be summed. Alpha can be left and right, I and J can be, let's say, plus or minus, okay? So it's this effective spin sitting here talking to this neighboring conduction electrons, okay? So this is the impurity. Of course, this is not the proper basis because if I want to diagonalize the conduction electrons, I need to go to momentum space. Okay, I need to go to momentum space, and then you have to recast the way we wrote yesterday for this, K and K prime. So this is going to scatter the conduction electrons as well. Okay, this is the Kondo model. This is the Kondo model. And more than that, this is called a Kondo model for a single impurity. For a single impurity. And also, it's the single channel model. Single channel. Single channel just meaning that there is one peculiar combination of conduction electrons that actually talk to this effective spin. We're going to see, it's going to become clear what is going to be 2, 3, 4 channels later when I actually have more than one combination here talking to the conduction electrons. But so far, this is the proper combination. The number of channels is more subtle, but I think it's going to become clear in a moment. It's basically the different number of hybridization profiles that we have. They have to be different by symmetry, and here we just have one. Okay, but I won't explain in all details the phase diagrams of Kondo models. We won't have time for this, because I also want to cover some other topics today. But I will tell you that the single channel, single impurity model is extremely well understood. The case of impurities, even if you have more channels, they are also understood. There are very good techniques that can be used to handle these systems, both analytically and numerically, including even bosonization, because this is an effective 1D problem with this impurity here. It includes also numerical renormalization group techniques and so on. And in this case, the two-channel is already significantly more interesting than the single-channel one. The critical behavior, the two-channel Kondo impurity case. So here, if I have, let's say, 2 channels, I already say what this is not. This is not 2 channels or more. If you have 2 channels, this would have a JK1 and JK2. Both non-zero. And when the JK1 is equal to JK2, you have critical behavior. It's quite interesting, with quite interesting properties. I will not have, this would be one lecture to explain this. I won't have time, but keep in mind that when, again, you have energy scales that are competing, same as the case for the magnets, this is where the system, it's very hard for the system to decide what to do, or it's very hard for us to understand what the system is doing. The system will just do whatever it wants to do. But this case is when you can get, these are cases like this is when you can get very interesting physics, okay? So when these two are comparable. But in nature, they are not typically comparable, okay? They are not typically comparable. So how can you make them comparable, okay? As usual, the suspect is written here. So I wrote down how to, they can become compatible or comparable. It's by doing Floquet engineering. Okay, so in cases in which JK1, JK2, for example, are very different, as it is the case here, as here, JK2 is 0, we can do Floquet engineering. This is the main message here. Okay, we can do Floquet engineering. I didn't write down what is the J condo here. This can be calculated when you do the Schrieffer-Wolff, and again, quite similar to the Heisenberg case in terms of algebra. Jk is going to be proportional to v squared divided by absolute value of epsilon f. Okay. Same spirit. This v here is basically doing the role of the hopping that we had yesterday for the magnetic models. And epsilon f is basically doing the role of the Coulomb repulsion. Okay? And before we had these virtual states for the magnets in which you had 2 electrons in a single site. It's also the case here. You pay this epsilon f when? Well, you cannot put 2 electrons here, impossible. You take U to infinity, 2 electrons out of question, completely out of question. But you can somehow, this electron can visit the neighbor and come back, maybe. Visit and come back. These are called valence fluctuations. These are valence fluctuations. This is just a dot, but if you have a real atom, this is the case in which this atom that is representing the impurity is going to lose 1 electron. So the valence of the atom will fluctuate, like from 3 plus to 4 plus, for example. Some atoms have a valence, well-defined valence, and then it fluctuates, okay? This is, again, very realistic for F electrons, if you go to the periodic table. In particular, models like this, the Kondo model is the low energy description, for example, of cerium, materials that have cerium, maybe praseodymium, okay? Even though it was first proposed for d electrons, but d electrons are slightly more complicated. But for F electrons, so if your impurity is, let's say, cerium, this is a this model describes well the low energy physics for this atom in a conduction electron environment. Okay, so if you make this gas of electron and put your cerium atom there, this is the model that you get. But again, you get it typically with 1 channel only. But 2 channels is significantly more interesting. So I'm going to just give you the protocol that was suggested first for this particular model here. I'm following this paper basically verbatim, like I'm really following the notation. Then we can generalize it a bit. This paper is Eckenstein and Werner, so it's archive 1704. 032300. This is where this was first proposed, and I'm going to follow the same protocol. You can drive it with delta 0 sine of omega t. Sorry, 1704 0300. You think it's missing 1 number here? Okay, 02300. It should be this one, otherwise I will also link this to the web page, but in my notes I have this number here, okay? All right. So I sigma AI L sigma dagger AI L sigma minus, and this minus is important, AIR sigma dagger AI R sigma. This is our drive. This is an oscillating chemical potential. So in a sense, what you can do, you take your drive, you shake these electrons a bit. You shake these electrons here. These guys you're going to shake. And these guys you're going to shake as well. But you shake them out of phase. Out of phase, okay? So this is, if you move this sign to the inside the sum, this term and this term are out of phase because we have a minus factor in the middle, so it's a pi phase. So this is an oscillating chemical potential with a minus sign in the middle. Questions so far? We can make this driving protocol very similar to what we had yesterday. You can say, well, now we have an oscillating chemical potential, but I became an expert in solving problems in which we have the parallel substitution, not the oscillating chemical potential. Well, it turns out that these 2 models are basically the same model. So what I'm going to suggest, this was also suggested in this paper, is to perform a transformation to a rotating frame. So if you go to a rotating frame, and we choose the following unitary. If our unitary is u of t is equal to exponential of I. You learned this from the exercise. At this point, you should know exactly what to do to eliminate this term, but you're going to pay a price. You're going to pay a price. But as you solved in your homework set, you just take the integral of this term as the rotating, when you go to the rotating frame. So if I call this hi, and I want to eliminate this driving term completely, I just take exponential of I delta 0 divided by omega times cosine of omega t h1. If you just, as you did in your homework, if you just perform this transformation, you eliminate this term. Fine. But that's good news, actually, that life is not so simple, because now, even though the dot will not feel anything, the dot is feeling fine, but the hybridization term and the lead term may suffer the consequences. I will leave you to perform this rotation as an exercise because I won't have time, but it's identical to what we did during the lecture. And the important thing is that the hybridization term changes. The hybridization term changes to the following form. Sum over V, e to the I phi of t, sum over sigma, C sigma dagger A alpha sigma plus, so it's at position 0 plus A 0R sigma dagger C sigma, all of this plus the Hermitian conjugate. Okay? So this phase is going to change both this and these terms, and then you still have to take the Hermitian conjugate to have the full hybridization term. It's a simple exercise. You're going to do again, I gave you all the ingredients earlier this week. You have to do manipulations with fermions again. These are all fermions. So this is how the hybridization changes. Phi of t, I'm defining as eta cosine of omega t, and eta I'm defining as delta 0, sorry, omega here, omega t divided by omega cosine of omega t. Looking good. Our hybridization now has a time dependence. It's looking good, yes. Oh, sorry, there is not. Thank you. Yeah, I was just rewriting. Sorry. Yes, thank you. More questions? All right. Okay, so now we were able to move by this rotating frame. We have a phase here. So as I told you, and I'm going to tell you more details, 2 channels or more channels we are going to have when we have different hybridization profiles. And then you say different, how different? They have to be different by symmetry. Otherwise, they add up to the same channel. But symmetry, what's symmetry? I will tell you in a moment. The answer is going to involve group theory. They have to transform differently under the reducible representations of the lattice group, for example. All right. Now we can do the Floquet technique. We are completely ready. So we have an oscillating phase. We know how to do this. You can already start fearing that you are going to see some Bessel functions, and your fear is completely justified. Bessel functions are coming now. So we can decompose this hybridization term into components. I'm going to call them, it's more common to call them Vn. This is the hybridization component. It's going to be, again, let's do the Floquet theorem, or even if you prefer the Floquet theory, okay? And then you get Vn. which is V Bessel function of order n of eta times sum over sigma C sigma dagger. This is going to be the interesting part. A0L sigma plus e to the I pi n A0 R sigma plus e to the I pi n Hermitian conjugate. You may object that if I'm writing this phase times the Hermitian conjugate, Vn is not going to be Hermitian. You're completely correct if you make this objection, but recall that Vn dagger is V minus n. This is the condition to be fulfilled. Interesting thing here, the phase. This phase is interesting, okay? This phase is interesting. Where is it coming from? End of the day, it's coming from this minus sign, okay? This minus sign is such that this term and this term, they are out of phase, which is already reflected here. It's already, you can see that the combination with a phi involves the A and A dagger, and then the Hermitian conjugate will have the opposite sign. All right, but now, depending on n, we have two different possibilities for the hybridization. So we better define n odd and n even, okay, as two different things. As two different things. Vn for n odd has the following form. Square root of 2v, Bessel function n of eta, sum over sigma, C sigma dagger, B, a new fermion, 0, odd, sigma, plus Hermitian conjugate. And V even will have the following form. Square root of 2v, Bessel function n of eta, sum over n, sum over sigma, C sigma dagger, B odd, B even, sorry, sigma plus Hermitian conjugate, where B even and odd are defined exactly how you would expect. They have either a plus or a minus sign. It's a linear combination of the previous fermions with either a plus or a minus sign. Let me define them here. So B, 0, even or odd. Sigma is 1 by root 2 AI L sigma plus or minus AR IR sigma. Okay? Even with a plus sign. So I have two different combinations of fermions. They have opposite parity. Okay? Opposite parity. These are two different channels when you perform the Schurifer-Wolff transformation. This is some, knowing that these are different channels is something that you have to know in advance before performing the Schurifer-Wolff. So we had one channel now, but now we have two combinations due to the minus sign here. And all the Floquet sectors that are odd contribute to the same profile. This will be all added up. If you perform the Schurifer-Wolff transformation, remember, we are going to do it now. We can call it Floquet Schurifer-Wolff, in which we are also going to integrate out these n degrees of freedom. All the n's that are odd are going to add up. All the n's that are even are going to add up. This is going to lead us to the Kondo coupling 1. This is going to lead us to Kondo coupling 2. After we perform the Schurifer-Wolff transformation, okay? Questions so far? No, it's not a light this time. You just think of these electrons here and the electrons here. It's an oscillating chemical potential. It will be like a gate, They oscillate, but what is interesting, and it's a good point, what is interesting and very important is that you're going to oscillate them out of phase. So you take these guys and you do this. This minus sign is important. Otherwise, it's just the total number operator here, and you won't gain much. Another question that you could be asking me is, what is happening to the conduction electrons that you had here? You're completely neglecting them. That is true. You can this transformation, you can use this transformation as well to transform all the conduction electrons. That is fine. That is fine. This is an unitary transformation that can be applied to the conduction electrons as well, such that you rewrite everything now in terms of Bs. Everything now is written in terms of Bs. Okay. So the Kondo couplings are going to have the following form. JK, 1 or 2, is going to be our famous 4V squared. You cannot avoid the 4V squared divided by epsilon f. Sum in which L is either even or odd, depending if you want channel 1 or channel 2. JL of eta squared divided by 1 plus omega tilde. Sorry, now I'm using this omega tilde L, where omega tilde is going to be equal to omega divided by epsilon f. So we have, again, a dimensionless number. We can play with the dimensionless number. We have the same structure as before. Same structure as before. Here it depends how you define to get the plus or minus. If I put the minus yesterday, you can also put the minus. It's going to sum over all integers. It's not going to be, you're not going to get any difference if you put minus or plus here, because if you put a minus L here, this absolute value squared is even. Yes? The Floquet theorem where? Right. No, you do. You have to transform these terms as well. You do have to transform these terms. And depending on your protocol, you may have time dependencies in this term. But then you have to argue that these conduction electrons have some energy scale as well. That is if these are conduction electrons, you have an energy scale that is the Fermi energy. And then it's going to be a game that you have to play, and it's important. I will leave you. We can discuss during the coffee break. Let's say you apply this protocol, and then you have to do the unitary. You have to do this unitary for everybody. You have to do this unitary for everybody. But this is a number operator, right? This is the total number of electrons of L type. And this is the total number of electrons with R type. They individually commute with the hopping Hamiltonian. The hopping Hamiltonian individually preserves the number of left and right movements. That thing you can just commute and eliminate. Okay? Sometimes you cannot do this, and then you get phases here that you may be able to eliminate by using the idea that you have a Fermi energy here, some epsilon f, and then you have to compare this epsilon f with your frequency. If this epsilon f is significantly different as compared to your frequency, the conduction electrons will not feel anything. They feel very little. They feel very little. So sometimes, and this is the beauty of having these problems with strong correlations, you have more energy scales. And then you have to play with all of them. The one that I didn't tell you about is this big epsilon f, the Fermi energy of conduction electrons. You surely have a Fermi surface of some sort, because you have conduction electrons. But I didn't tell you about this energy scale. It does play a role here in general. So that's a good point. More questions? I suggest you have all the technology to perform this unitary here, okay? Just do it. You're going to use the so-called Baker-Campbell-Hausdorff formula. Or another tip that I give to you if you're talking about fermions and you want to do this, remember the fermions have very few states. So you can just guess what is the result, because you have such a tiny Hilbert space or Fock space that you can just guess when you apply this, let's say, U dagger to some term here U, you can just kind of guess what is going to come here. Okay. But if not, you can use the Baker-Campbell-Hausdorff equation. Okay, so again, we have everything that we wanted. We can make a plot. We can make a plot, and as a function of eta, we can plot the JK1. Let us do it. So it is going to look something like this. So this is going to be JK1 divided by JK stationary in our notation. This is what we had before, it's just this. And the odd one is going to do something like this. And at some point here, they may cross. They will cross. Okay, so this is JK2 divided by JK stationary. So you can tune, you can engineer eta such that you get a point in which these two channels are the same, or they have the same couplings. And again, the problem that I will not solve here during this lecture is the problem of how to understand the low energy physics of a model in which the two couplings are identical. This problem is critical. This problem has been solved by many different techniques. It will be another mini course to solve these problems, okay? But the point is very clear. The point is that now you have two couplings, two Kondo couplings as opposed to one. I would like to emphasize once again that the most important physical feature is this. Okay, after that, you divide into two different sectors, and this problem, if you give it any expert in this field of strongly correlated system, this hybridization, the person will immediately tell you what the Kondo couplings are. Okay, it's just the non-trivial aspect is to have two distinct hybridizations, and again, by distinct, they have different parities in this case. Questions so far? Of course, you can take this impurity case and do many, many other things. You can change the protocol. But more interestingly, you can consider the lattice case. I won't have the time to do details here, but this lattice case is part of my work with Rebecca Flint. And let me briefly show you what happens. So if you have a lattice like this, so here I'm representing one impurity again, but you have a sea of conduction electrons, but you should think of this middle ball here as a lattice of this middle ball, of these spheres here. Okay? It's a lattice of, let's say, zero atoms in an environment in which you have conduction electrons. And then you play the same game here, but we did it with light. So you have light perpendicular to the sample. You do it with light. And then you discover that you have instead 4 possible hybridization profiles. 4 possible hybridization profiles. So you're basically dressing the conduction electrons. That's what you're doing. You're dressing the conduction. They got dressed. So they behave like different. Here they behave like, let's say, S and P wave electron, or S and D. This is 1D. But if you have the lattice, you're dressing the conduction electrons, and then they now have 4 different flavors. Okay, this thing is not going to work. Okay, it's working again. So you have the S, that is the initial type of electrons, and then you have P plus, D wave, and P minus conduction electrons, 4 flavors. And they have different energies, and then you have to add up all the possible valence fluctuations of these 4 types, and they transform clearly differently. These are, if you are familiar with group theory, these are gamma 1, gamma 2, gamma 3, and gamma 4 are different E-reps, in this case of C4. So these are E-reps of the C4 group on a square lattice. You add them up, you get 4 Kondo couplings, okay? And then you can do the same trick. You can make 2 of them equal, 3 of them equal. It's a very fun game to play. Very fun game to play, okay? But this is the basic idea. It's the same as we did for 1D, but you can make it here I'm starting with the simple S-wave electrons, conduction electrons. You can do it for more complicated systems. You can take for example, serium compounds and just make it very realistic. It's okay. It's okay. Mm-hmm. Uh-huh. The what? No, exactly. I'm going to get there. It's my next. I can jump it a bit. Okay, this is. You can. Let me. I think I have a slide that answers your question precisely. It's this thing here. So when you, I'm not going to have time to tell you about details, but for each polarization of light, you can find what is, again, the symmetry group that is left. So I'm going to introduce this called a point array sphere here. I'm going to introduce it in a moment. But for each polarization of light, you can ask the question that you're asking. What symmetry is left? Because it's not a fair game to label the hybridizations according to symmetries that you don't have. And light is going to break some symmetries. So initially here, in this square lattice that I'm telling you, that I showed you the slide, it had C4V. But then circularly polarized light broke it down to C4. The mirrors are gone. So then I have to classify the E-reps according to the C4 group. And depending on polarizations, you can see I won't have time to go into details. You can have C2 left, C2V left, and so on. And then if you have only C2, for example, you're going to have very few channels that are different by symmetry, because then you have to sum all of them together. So you need the proper symmetry group to tell that this is different from this. It's a very important point, and brings me to something that I would like to discuss anyways. So here, I'm just showing another example that we had these 4 possibilities, in which we had these 4 possibilities. I won't have time to explain what is average over linearly polarized light. Maybe I will, I don't know. But then you can just see that the same idea applies. So you have crossings here, and then you can have crossing here, and so on. So you can really engineer, starting from one channel, you can engineer more channels. The main question is the existence of a plateau. So this, for sure, exists in calculations, but you have to be very careful about energy scales. There are a bunch. There are many energy scales. I already told you some of them. So epsilon f is an energy scale of the problem. This ratio, or v divided by epsilon f, has to be small. It's a dimensionless parameter. This difference here is relevant, and so on. This is a very interesting object. It is these are 4 channels, but 2 of them have exactly the same amplitude or the same value by symmetry. But these are 2 channels. It's basically because I'm representing here these 2 possible green objects. In this case, the C4V has a 2-dimensional E-rep. That's the answer to your question. So it's 2 couplings, if you will, but even more interesting, it's a 2-dimensional E-rep of C4V that by symmetry would have the same couplings, okay? All right, more questions? Yeah, so here, this is S-wave, basically, this is D-wave, and these are 2 P waves. It's P, in this example, it's PX and PY, but I'm choosing some light profile that, for this light profile, PX is equivalent to PY, so, and therefore it's a 2-dimensional E-rep of C4V. Okay, so that's what I had to tell you about the Kondo problem. Do you have more questions about this? Okay, so now for the second part of the lecture, I will briefly talk about, in terms of strongly correlated systems, I will probably come back last 5 minutes of the lecture or so to show you some new frontiers that I consider to be interesting. It's related to polarizations and so on, and it's also more related to something that I did. So I'll take 5 minutes for that, last 5 minutes. But for now, I want to go back to some basic topics that I didn't address so far. And these basic topics are the following. I want to know, first, how the system evolves in time, a Floquet system evolves in time. So far, I talked about this Floquet Hamiltonian. But can I write down the time evolution for a Floquet system just by exponentiating the Floquet Hamiltonian? Can I do that? The answer is almost, but not really. So I have to address how would I evolve in time a system that is time periodic? And then I want to talk very briefly about this quantum limit of light. I find this to be interesting. I just want to highlight one or two things. In other words, everything that we are doing here is classical in terms of the electromagnetic field. This is classical electrodynamics. But if I go to a cavity, even a dark cavity, in which the only photons that are there are quantum fluctuations of the vacuum, or very few photons, can I do all of this? And can I recover this limit by going to coherent states or any other limit in which I expect light to become classical? This is also a new frontier. So this is what I will be doing for the next 40 minutes or so, okay? So let's start with time evolution. Okay, so now I want to slightly tell you briefly about how a system evolves in time. All right, so our topic now is the time evolution. Of Floquet systems. Okay. Before I tell you this, I just remembered let me tell you something about also the Kondo lattice, because I'm showing just the results for the Kondo couplings. There are several cases that are not understood in terms of several compounds which form Kondo lattices that are not understood. We just don't understand the phase diagram. So while for the impurity we know more or less, or we know how to solve the impurity problem, numerically, analytically, and so on, the Kondo lattices we don't know how to solve. The multi-channel Kondo lattice, we don't know the solution to that problem in general, okay? So I would say that the main motivation to do this, in this case, is to access these phases of matter that we cannot completely understand. And these phases of matter appear particularly, again, when the couplings are equal. You have several proposals for these phases, but they are very hard to find experimentally. But Floquet engineering is a possible way of tuning these couplings to be equal, and this is going to naturally enhance those weird or hard to understand phases. So that's the basic idea. So I'm giving you a precise example in which we just don't know how to solve the problem. And we would really like to know how to solve this problem. But the first thing is we want as many experimental verifications as possible of those phases. And these experimental realizations or verifications could come from protocols like this. Okay? So for the lattice, the Kondo lattice is one of the problems that we don't know how to solve in general. Okay, now back to the time evolution. We know that in general, if you write down Schrödinger's equation, we know how to evolve that equation in time, at least formally. No, the 1D we know better. The 2 and 3 dimension, all these rare earth compounds present phases that have possible descriptions, and we know how to find phases for these materials, but we know how to find phases by using mean field and other techniques that are not exact for sure. So I'm not going to have time, but our motivation here was this composite order scenario for these two-channel lattices and how to enhance critical temperatures and so on. I won't have the plot, but you can enhance critical temperatures significantly for possible orders by doing this, okay? So you can increase TCs, basically. You have some superconducting phase that is proposed, and this protocol could increase TC by a factor of 5, let's say. This would be very desirable, experimentally. Okay, so we know how to evolve problems. So if we have Schrödinger's equation, we always can write it down as psi of t is I dt, psi of t, And we can evolve it in time formally. It's formal, but at the end of the day, it's not particularly useful. So you write down the time evolution operator from t0 to some time t as the time-ordered exponential of minus I, the integral from t0 to t, d tau, let's say, h of tau. If you have a Hamiltonian that does not depend on time, the Hamiltonian is, let's say, a constant. It's a matrix or whatever. It's an operator that this operator commutes with itself, and you can just integrate this. The time ordering is harmless. But if not, you have to expand this exponential order by order in powers of this integral. You're going to get many integrals, and then you have to time order. Time ordering just means that you order the times. Okay, so if you time order two objects, the times have to be ordered in ascending order. Okay, very good. And we have an important property here that we can use, that our Hamiltonian, as a function of time, is periodic. It's periodic. These are the rules of the game. So now you can ask the following question. Can I just come here and replace this maybe by exponential of, this would be the dream, minus I, h Floquet, t minus t0? That would be great. Okay, let's see. Let's say that you have, and this is going to be a bit hard to draw, but let's see. Let's say that I have, this is a function of time, and then we have something that looks like this. Okay, some periodic potential. I don't want to draw a sine or a cosine, because otherwise you can think, well, it's always like this. No, it's something periodic. It can be a bit strange. Okay, and then I fix some time t0 here. And this is going to be, therefore, t0 plus the period. The answer to the question that I won't have time because we're running out of time to answer is the following. If I want to, given a time, to evolve it by one period, then I can use the Floquet Hamiltonian. So we say that the Floquet Hamiltonian is responsible for the stroboscopic evolution. So it brings you from here to here, from here to here, from here to here as well. But if instead you want to evolve it just for a tiny bit like this, the Floquet Hamiltonian is not going to be sufficient. By a tiny bit like this, you don't even know for sure if this Hamiltonian is periodic in time or not. You're just here. You don't know. Okay, with this information in mind, with this picture in mind, but for sure, physically, you can evolve for how much time as you would like. So physically, there's no problem at all in asking what is the time evolution from this point to this point. And there is an operator here, u of t0. Okay? I will give you what the answer is, and we can discuss during the coffee breaks how to find this answer. But the point is that to evolve in time, you're going to need to combine your Floquet Hamiltonian or your Floquet evolution with something else. And the answer is this. The time evolution from t0 to t is exponential of minus I kf of tau is exponential of minus I hf. Sorry, let me write it t minus t0. Or this is the good old Floquet Hamiltonian. And this is called the kick operator. This is something that we're introducing now. It has not been introduced during the week. And you can find, by plugging this into Schrödinger's equation, what are the equations followed by these operators. But what I will tell you is that this part has the following property. E to the minus I kf of t plus the period is equal to e to the minus I kf of t. This comes back to one of the first questions that you asked during the week. You asked me, well, you're doing this Fourier decomposition, Fourier series for this periodic potential, but if I recall from solid state physics, when I learned Bloch's theorem, I don't need to do this. I can write everything down in terms of operators, and I can say that I have a symmetry, the lattice symmetry, and then from the lattice symmetry, I know that momentum is the variable that is conjugated to the position, and I can find what are the possible values. I can find basically the Bloch's theorem from that. This would be the analog here, okay? A periodic function in time times something that is left. What is left is this Floquet Hamiltonian, all right? So this is how the time evolution is given. I won't have much time to explore the form of HF. It may not be unique, actually. It may have this T0 dependence. And, some people call this T0 the Floquet gauge choice. It's a fancy word, but just to tell you that the evolution depends from the place where you start. But you expect energies and anything that is meaningful to just be a function of this time difference. Okay? If I start from here to here and so on. Sorry, yeah, this is bad notation, I'm sorry. This is a function of t, but this is not. This is times this, and this is function of t. It's a function of t. While the Floquet Hamiltonian is time independent, and it will just evolve it by this much. Questions so far? This is identical, the whole thing is identical to this. I'm not sure how to do this separation very simply. What I would do, I take this into Schrödinger's equation, I take the derivatives and so on, and Kf is basically, you're going to see that Kf is basically playing the role of this rotating frame. It's basically the equation that HF will fulfill is basically, we don't have time ordering anymore or objects that don't commute. But the equation followed by this HF, you can find it. Not necessarily. No. Okay. So if you want to do dynamics, as it was the topic during this Minicourse, what you're going to do, and this is even harder to draw, you're going to have the envelope that is described by Floquet engineering, and then you're going to have oscillations around this envelope. So, and here I will be very general, and I will give a reference as well. So maybe I can start by being general first, I guess. If I want to find the value of some observable, as a function of time, I will have some envelope here, but then I will have oscillations here. Oscillations around the envelope, and these oscillations are due to terms like this. When you're in any problem that you are going to, I always suggest you, if you have a simple enough problem, do the exact time evolution and compare. Then you get some intuition of what's going to take this. So a homework that, if we had 2 more weeks, let's say, in this mini course, a homework for next week, I would say, would be to take the spin half problem and just or a two-site problem, just solve it, do the Trotter decomposition, do it your favorite way, find the expectation value of some observable and compare with what you're getting from Floquet theorem, or from Floquet theory before today, because until today, we were not addressing this. You're going to see basically an envelope with these oscillations on top of the envelope. Again, this is completely reminiscent of Bloch's theorem for crystals. All right, so let me see if I can, okay, go ahead. Yeah, this is what I call this gauge. There is this gauge structure. So what you're asking is, if I add some time here, it's going to come back to itself, but how do I know which is the first original best choice of this T0? This is a gauge choice. This can be, you can move it around by the starting point of your evolution, you can move around by gauging it, like you keep pushing it. No, you can just take this thing here, plug it, and you're going to, the choice of KF is not unique, actually. I mean, you're going to, the KF follows an equation that is basically this rotating frame equation. The choice of KF is not unique, but it affects the choice of HF in a sense. So I'll leave you, we are not going to have time to do this, but try to do this for a spin half. Just take your spin half. We found the Floquet Hamiltonian and so on. Try to evolve it in time. You can even evolve the spin half in time by just coming here and solving this problem. This problem for a spin half is not hard. And then compare both approaches and conclude what is the form of KF. But this is it's a more sophisticated exercise at this point. Okay, but we could do this. I will leave you with a reference. These are lecture notes. It's probably a Boulder course, I'm not sure. This is the author. And I will put this as a reference, but I think this is these observables and how they evolve and how they oscillate on top of the envelope. These are lecture notes by this author that I found to be very useful with many drawings, okay? I'm following basically their approach. Okay? All right. I will not do the derivation coming to this point. It's several equations using many times this property here. Recall that if we don't have this, we obviously don't have this, okay? So it's just, the only thing that you have to use is that the time evolution forms a semi-group, which just means that you can break the evolution from some point here to some point here. You can just stop here. You can make a quick stop or an instantaneous stop. You evolve from here to here and then from here to here. The time evolution operator satisfies the property that if you want to come from here to here, you can make a quick stop here and then it factorizes as one time evolution operator for here times the next time evolution operator from here to here. You have to use this multiple times, you get to that result. We can discuss during the afternoon if you're intrigued by this derivation. Okay? All right, so this was the first thing that I would like to at least quickly address before we end this mini course. The next thing that I would like to address is going beyond the classical limit of light. I find this to be quite interesting. So let me propose what is the problem first. The problem now, so this was what I had to say just about time evolution of Floquet systems, let's say n observables. Okay. Now what I have to say next is about beyond classical fields. So to go beyond classical fields, I can propose the following. The the following problem. So let's say that I put here the number of photons. So when the number of photons go to infinity, I may expect, but even that expectation is a bit strange, maybe, to get the classical limit. Classical limit that we have been doing this entire week. I say that this expectation can be slightly strange because we know that the classical limit of light is through coherent states that don't have a well-defined number of photons. But the distribution is not that broad. Okay, so you reach the classical limit by increasing the number of photons, let's say. And when the number of photons is 0, you have a dark cavity. Dark cavity. Only the quantum mechanical fluctuations of the vacuum will play a role. It will be very desirable to come from here to here in a way. Is it possible? It involves doing all calculations quantum mechanically. You have to take light, you take the classical field, light, and you quantize it. And you quantize it. Of course, the calculations are not going to get any simpler when you do this, okay? Now you can quantize, you can call the second quantized operator A and A dagger. These are the quantized operators for light. And again, I will put all the references for this mini course. I will upload them to my web page later, probably over the weekend, but I can already include some of the most important ones here. This was done in PRR 2033033 from 2020. And since then, this quickly exploded. I mean, many proposals followed this initial one. Okay? The idea schematically is that I have H classical, which is not by all means a classical Hamiltonian. It's a quantum mechanical Hamiltonian with classical light. And I will call this H of Q of t, where our Q of t, for instance, could be our good old A0 cosine of omega t, let's say. This is basically what we did. We took a classical model, or a quantum mechanical model with classical light and made it time-dependent and periodic. And now I will promote this. I will promote this to H quantum. H quantum. Yeah. Yes, precisely. Time dependent, spatial dependence, or even you can be even less. You can even consider a quantum dot first. Just put a dot inside a cavity, and then you just want to know what is happening to the dot in that particular position. But what I will be doing now is, going back to Neto's question, is much more dramatic. I will be considering a single mode, single photonic mode. And I will say that H quantum is H within the dipolar approximation of G A plus A dagger, where this is not even a function. This is times, okay? I'll just promote this to G times basically X, like a dipole type of thing, plus omega A dagger E. So this is going to be my quantum mechanical version. A will have dynamics by itself. Okay, it's a quantum mechanical operator. It will, if you write down the, it's a free field. If you write down the equation of motion, let's say, for A, you acquire the exponential behavior with some oscillation automatically. Okay, it's going to, the oscillation frequency is going to be related to this G. But it's a quantum mechanical object, and therefore it has its own time evolution. Then you can take this form and solve the problem. Okay, maybe. solve the problem. So can you speak a bit loudly? No, it's just the simplest problem that can be solved first. Let's solve this simple problem first. Yeah. Yeah, no, monochromatic light still has a dispersion. Has modes omega of k. It's just as we can follow as Einstein did first when he was solving for the optical modes, let's say. Or we can just consider one flavor. That is already interesting. This is already an interesting protocol that we can try to solve. And let's write our H quantum the following way. H quantum, I'll bring back this J. But maybe I will write TH. Since this week we converged to using TH, why not? Sum over I and sigma. Cj sigma, dagger, Cj plus 1 sigma. And then you can say, well, maybe now you're going to put some exponential and it's going to become a Bessel function. Hopefully. Because so far we are going to have an exponential of a quantum mechanical operator. So can we ever recover in this classical limit the Bessel function? Now we're going to be missing the Bessel functions, okay? All right, so this is e to the IA, where A is G of A plus A dagger. You could take this as a toy model and just see what happens. Okay, this is. Oh, sorry, yes. Sorry, J. Okay. Plus Hermitian conjugate plus omega A dagger A. We are considering a 1D chain coupled to this thing, like a dipolar type of coupling. Okay, it's really raining again. This can give me a bit of some extra minutes, I guess. Okay. All right, so I will propose the following unitary transformation. So we are going to a rotating frame. I want to at least eliminate this, even if it costs me something. But I want to eliminate this. So I go to a rotating frame to eliminate this term. So I will rotate this, e to the I omega t A dagger A. It will eliminate this term. It will not do much for the other terms, but these calculations I won't necessarily do. So when you go to a rotating frame, you have to perform the unitary here. You have to perform the unitary here. But then recall that the A, big A, is A plus A dagger. You have very convenient identities to handle such cases. One of them, if you took quantum mechanics from Cohen Tanuji's book, is called Glauber's equation. To no one's surprises, Glauber was working with quantum optics. So this is precisely the type of identities that you need to write down if you want to solve this problem. So just to be precise, I have this. Or you can do this so-called Glauber expansion, but there are more. You can do the Glauber expansion, you expand A, and then you resum. But there are identities that are meant specifically for this case, in which this is e to the I G plus A. It's basically related to the fact that the commutator of the number with A or A dagger returns back A or A dagger up to a minus sign. Okay? From this point on, I will leave you as an exercise. Again, if we had a second week, this would be the beginning of second week, but we don't. So I will leave you to finish this calculation as an exercise, and you find very interesting results. Very interesting results. And you can ask me during the coffee break about these calculations, okay? I've done basically all of them. So just what you need to use is A with A dagger A, for instance. You're going to use this is equal to A, and so on. And then you discover that you can take expectation values of this quantum Hamiltonian with respect to this number operator. But already rotated, H, let's say, rotated expectation value in which A dagger A of n is n. Okay? In the end of the day, this is a one-dimensional harmonic oscillator for A. Okay? And then you're going to discover that here, what is going to appear, and I will leave you, really this is an exercise, this is going to become the Taylor series of J0, the Bessel function, if you assume that the frequency is high enough. Again, I don't have time to do the calculation, but this is how we recover the classical limit. It's going to become in the classical limit, after you take this n and n large, here you're going to have a huge Taylor series, and recall that A and A dagger do not commute, so you have to Taylor expand this and so on, and a bunch of binomial terms, and then you take expectation value. It's just algebra. It's many, many steps. You recover the Taylor series for J0 in the limit in which the frequency is high, which would correspond exactly to what you calculated when you were solving your homework for the high frequency limit of the classical model, okay? So this answer is going to be the same answer as you calculated in the classical case, which shows that you can actually interpolate from the dark cavity limit. You can do few photons here, and then you can go all the way, when the number of photons is large, to the classical limit. You can recover the classical limit. Because I want to see at least one Bessel function appearing in front of me. And otherwise, this series is going to become more complicated. But you have more than one parameter here, right? Sorry? Yeah, that's right. It should be, yes. In this particular limit. To be completely frank, in the limit of in which you take a coherent state, which is a coherent state is a superposition of many number of is a linear combination of terms with a definite number of photons, but that limit should recover what we had before. I will leave you as an exercise to do this. Let me just see if there is anything else that I can tell you about that doesn't require a lot of algebra. Yeah, everything else requires lots of algebra. You have to rotate this first. That is okay. But then you have the exponential of a bunch of A's and A daggers that you have to expand as a Taylor series and then resum the Taylor series. So these are the basic steps. Questions? I think this is an interesting, so this same paper already addressed the simple Hubbard cases. Then it becomes significantly lengthy, but Are you asking if the expectation value of the coherent state would also work? Is that the question? It would. Yeah, it would work. Yeah. Yeah, here the understanding is that even though the classical limit is reached with the coherent states as expected, if it doesn't work for the coherent states, something is off. But the point is that it works even with this number of photons being fixed, because the distribution, if you look at the coherent state, it's a state, and then you look at the distribution of n, the number of photons, it's a Poisson distribution. So it's not very large. So that's why probably this is okay. Questions? Yes. Uh-huh. Or are you asking if we can also stay in the quantum limit? Yes, exactly. So the idea, this was solved before. You can solving, as I told you several times this week, solving here is not going to be simple. It's never simple, or it's often not simple to solve here in the middle. This problem has been solved before. Then you can take the expectation value of 0 photons, end of calculation. But you can take expectation value with any number of photons here. And then you can find something. So you can project, basically. You say, well, I want to fix the number of photons to be 10. And then you do everything, and then you make this number equal to 10, and so on, and then you have an effective model that is going to be living inside the subspace when n is equal to 10. Okay? More questions? Okay, so I would like to finish by showing some slides very briefly about something that we have been doing in our group, and then we can go for lunch. So I already told you about this. Problem here. We basically did the required steps during today's lecture of how to solve this. This was done for circularly polarized light, as I pointed there. But in this case, as I told you several times this week, this circular light is going to bring some chirality. And sometimes this is not very desirable. But then I told you, well, if you don't want chirality, just choose linearly polarized light. But then we discussed, if I choose linearly polarized light, I will break symmetries. And I showed you before, if you break symmetries, the way you're going to classify, let's say, in your Kondo problem, the way you classify your hybridizations can become very poor. The same is true for magnets. If you break symmetries, it's likely that the system will magnetically order somehow, because you're choosing one direction with some preference. You're preferring one direction as compared to the other directions. So what we did, we first revisit this problem of fixed polarization, and if you took advanced electrodynamics, you probably heard of this. It's called the Poincaré sphere. So the Poincaré sphere gives you a way of representing all polarizations. So along the surface of a sphere, on the surface of a sphere, each point here represents one given polarization of light. You can choose your favorite polarization. It's going to be 1 point along this. So basically, the equator corresponds to linearly polarized light, North Pole and South Pole to circularly polarized light, and in general, elliptical polarization. But what you can do, and this is actually done in optics using depolarizers, you can start to walk around the surface of this sphere. You can have trajectories on the surface of a sphere. And if you know from electrodynamics that it means that light will no longer be monochromatic. Monochromatic light has a very well-defined specific polarization and should correspond to a point on the surface of a sphere, not a line, not anything. So these profiles are not exactly monochromatic. Then you have to redo and rethink your Floquet engineering. It's not going to be monochromatic anymore. It's going to be polychromatic. So life is not going to be that simple, but it's doable. It is doable. And again, you can choose paths on the surface of a sphere to recover lattice symmetries or to recover even this limit. It's called natural light. If you go, there's a limit in which light is completely unpolarized. It's called natural light. And you can recover these limits by going along trajectories on the surface of the Poincaré sphere, okay? And we did that. I won't have time to show the details. You get more complicated functions and so on. We even cooked up one profile here that interpolates along some trajectories, so you can do this analytically by considering 2 different frequencies with a small detuning, and then by changing this detuning and so on, and this number n, you can interpolate along the surface of the sphere. This is something that we did over the last years, and it's complementary to what you learned during this week, okay? So this is a general extrapolation going on the top of, or on the surface of this Poincaré sphere. So you can generalize everything here with light that is not monochromatic light, or more important is that the light doesn't have a fixed polarization, it's unpolarized. As a consequence, it's not monochromatic. You don't have lights without unpolarized light that is monochromatic. This is impossible. This is what we did over the past years, and then you can recover, and this is just a plot to show you can, as I told you the other day, you can change this exchange coupling, so you can make it chiral if you want. It's shown here. If, oh, but I don't want it chiral, you can change this number, and then it's not chiral again. You can play with these parameters, and then you can increase frustration and so on, and you can get the spin liquids, and you can get the effective Kondo models, okay? Just to show you in practice how this works. All right, so I won't have time. I already showed you this. Let me just finish by showing you our group in São Carlos. So this is, we have a very nice group there. Some of the students are here. Some of us are here. So Neto is here, I'm here. We also have other faculty there in our big theoretical condensed matter group. You can see here Chico Alcaraz, you can see Thais Trevisan. It's around here somewhere where, yeah, here's Thais, here's Krysia Zawadsky, and we have many students that are attending this school, or this workshop, or no, this mini course. This mini course and many students that are not. And I would like to finish by also advertising that I was recently awarded of a PESP grant that came with fellowships for students. So if you know or you're interested in Floquet engineering in general, we are always looking for motivated students, not only in Floquet engineering, but also in several other topics in strongly correlated systems in general. How to probe strong correlations, how to produce strong correlations, how to solve strong correlated systems. So let me finish with this small advertisement. And finally, let me finish by thanking the organizers again, by thanking José, by thanking Rui, by thanking Joy, and thank all of you for coming. It has been extremely entertaining, and I hope you have learned a bit about this topic. And if you want to do some Floquet engineering for your favorite problem, and if we haven't covered it here, you can always write to me, and you can go to the website. I will upload some lecture notes, some references. Also, these lectures are being recorded, so I will put links to the YouTube channels and so on. All right, do you have more questions? Go ahead. Yes, there are several other possible platforms. Yes, there are several other possible platforms. I showed you one case of this oscillating chemical potential, so you gate it with oscillating potentials. Fernando showed you a case in which you wait for some time and then you kick the system, and then you wait for a period and then you kick again. So this is the direct comb, basically. So you kick it, you wait, you kick it again. So there are several possible, we call these protocols. It's not only light. Light is convenient. The laser community already did a lot of theory even in these particular systems, but other potentials, we call it potentials. It's an external thing that oscillates in time. You can even take your sample and start shaking it. Like anything that perturbs the system periodically is good. And here, what I showed you in previous slides, that what we did over the past years, it's considered the limit in which it's not exactly periodic. It's a periodic potential plus something that breaks this periodicity. But it breaks it in a very controlled way. So just to show you this picture again, in physics, we really, in this field of strongly correlated systems especially, we really like these large N theories. N is a parameter in which the inverse of N controls some type of fluctuation or error or something. So we cooked up a system in which you break this time translation by 1 by N. When N goes to infinity, it's completely periodic in time. So it's completely periodic in time. But if N is finite, then you are breaking time periodicity by a tiny bit in a very controlled way. So this is a way of going beyond, breaking the time translation by a tiny bit, okay? Tiny bit, I mean 1 by n, where n, this ratio is dimensionless. That's what I mean by tiny. Mm-hmm. Mm-hmm. Right. It is possible. It is possible. But the thing is this. If you choose circularly polarized light, the Z2 becomes the Chern number, the Z. It becomes Z. Z2 becomes Z, because now you're breaking time in reversal, it's a Chern insulator. Graphene, in a sense, what we did was that. Graphene was proposed first by Kane and Mealy to have this Z2 invariant. It does not break time reversal. The thing is that it requires a spin-orbit coupling. In graphene, this is not large. But what we did was the other way around. We took graphene, no spin-orbit coupling, no nothing, direct cones, and then we put circularly polarized light and made it Z. The invariant is Z. We made it a Chern insulator. In principle, all of this is possible. Spin Hall effect, yes. So you don't want to break also symmetries for that. So this unpolarized light can be promising. Yeah, it's something that we have in mind. Yes, because the unpolarized light provides a way of not breaking symmetries, but also changing things. It doesn't bring chirality. It doesn't bring any lattice symmetry breaking. Sunlight, this light coming from the sun, is unpolarized. For example, this natural light. But it's not you cannot do Floquet engineering with that, because you want a unpolarized, but you don't want the frequency spectrum to be very broad. More questions? All right. If not, let me thank everybody again for coming, and the organizers, and see you around.